Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on November 2nd, 2025, about 8 days ago. This paper introduces a plug-and-play way to learn shortcut skills inside task and motion planning that cuts overall plan lengths by over 50% and consistently outperforms pure planning and pure reinforcement learning. The paper is titled SLAP, Shortcut Learning for Abstract Planning. And as we'll see later, the method discovers dynamic moves like slap, wiggle, and wipe that make long horizon robot tasks faster, with results that are really impressive. Alright, the introduction set the challenge and the premise. Figure 1 contrasts 3 execution styles under the same block stacking goal, which clarifies where the time savings come from. The left column shows the initial scene and the goal specification. The top row, labeled slap, shows a short sequence that picks the target, then uses a slap-like motion to clear space, so placement finishes quickly. The middle row for pure planning shows many careful unstacking steps. The bottom row for pure reinforcement learning shows flailing behavior that rarely achieves the goal. So Figure 1 showed why shorter executions matter. Figure 2 presents the abstract planning graph, which stacks a top layer of abstract states connected by options and a bottom layer of environment states connected by actions. The star marks the goal at the top, and the green arrows trace the shortest path through concrete states. This two-level view matters because planning minimizes execution time at the bottom while respecting the abstract structure above. So the previous figure outlined the two-level graph. Figure 3 shows the full pipeline. Panel A builds graphs and proposes shortcuts. Panel B converts each candidate into a shortcut Markov decision process. And Panel C trains policies in parallel with reinforcement learning so multiple skills learn at once. Panel D integrates learned policies into planning and prunes any edge that fails within a set budget, which keeps plans reliable. Panel E demonstrates generalization to new tasks and to different object sets via a relevant object state projection. Okay, the previous figure laid out the pipeline. Table 1 reports outcomes across 4 environments, showing 100% success for the shortcut learner and for pure planning, while the reinforcement learning baselines mostly failed and hit the maximum horizon. Plan lengths drop sharply, about 31% in Obstacle 2D, 69% in Obstacle Tower, 50% in Cluttered Drawer, and 66% in Cleanup Table. These reductions matter because the tasks remain solved while execution becomes far shorter, which implies real-time savings. So the previous table reported strong success rates and large plan length drops. Figure 5 shows generalization in Obstacle Tower, where training used 3 stacked obstacles, but testing varied both stacks and distractors. The left bar chart shows plan length staying roughly flat for the shortcut learner, while pure planning grows steadily as obstacles increase, which signals multi-object efficiency. The right panels illustrate object substitution, where relevant objects are mapped, and a slap-style shortcut moves the whole tower, keeping plans short. Alright, 2 takeaways stand out. Learning shortcut skills inside task and motion planning cuts plan length by roughly half while keeping success high, and the discovered moves like slap or wiggle give dynamic multi-object efficiency beyond hand-coded options. The broader implication is a practical bridge between planning and reinforcement learning that generalizes, though it depends on a good abstraction. Thanks for listening. I am Alex, and this was the AI Research Roundup.